Hi everyone. In this video, we'll explore some new applications of the definitions of norms and of dot products. The first one that we're going to think about is how to study the orthogonal projection of a vector onto another given vector. Here's our setup. I'm given a vector u and another vector v, and my goal is to project v down to u. In other words, to be more precise, what I would like to be able to do is to write v as the sum of two vectors. Here in the picture, you see that one of them is w, which is the projection of v onto the vector u. So we want to write v as the sum of two vectors. One is parallel to u, and the other is perpendicular to u. And if their sum has to be v, then one needs to be some vector w and the other one must be v minus w. So our goal here is to, given a fixed u and the vector v, how to find w. So w, we want it to be parallel to u. So w will be a constant times u. All we have to determine is what the constant is. Right? W lies on the span of u, so it has to be a constant times u. The way we'll determine what it is to use the fact that, well, we want v minus w to be perpendicular to u. So to determine w, we'll use two facts. The first is that w is parallel to u, and that tells us that we need to look for a constant c. And c is determined from the second fact, which is that v minus w is perpendicular to u. Let's see how. Writing that v minus w is perpendicular to u is the same thing as writing that v minus w dot u is equal to 0. In other words, v dot u has to be equal to w dot u. So v dot u, well, w, remember, we want it to be a constant times u dotted with u. But then I can solve for the constant from here. And I get that the constant is v dot u divided by u dot u. And this is more often written as v dot u over the norm of u squared, because those two quantities are the same. That's exactly what we get. The projection of the vector v onto u another vector u is given by a multiple of the vector u times the constant, which depends on the length of u and the dot product between v and u in this fact. Let's try to do it in an example. This is the situation. I have my vector v and I want to project it down to the vector u, which is, I want to project it down to this line here, the line parallel to u. The projection, as you can see in this picture, is the vector w that forms a right angle and it's parallel to u. It forms a right angle with v, well, with the projection of v, and it's parallel to u. The formula is given here, so let's write it down. Right? Let's write down what that gives us. The pieces of that formula are going to be the dot product between u and v, but this is 1 times 1 plus, 1 plus 1 times 2 plus 1 times 3. So it's 1 plus 2 plus 3 is equal to 6. The norm of u squared is just the sum of the squares of the components of u. So that's 1 plus 4 plus 9, which is 14. And therefore, w is given by 6 over 14 times u, which is 1, 2, 3. We can simplify this a little bit, but we can also leave this answer. That's our projection w. Okay. Last, I want to mention two important consequences of the definition of a dot product and of norm. The first one is the Cauchy-Schwarz inequality. It's written here. Whenever I take any two vectors in Rn, the absolute value of their dot product is always going to be smaller than or equal than the product of their lengths. The way that we can make sure this is true is in two steps. Well, first of all, I want to convince you that this is the case when we have unit vectors. The unit vector setup is right here. You should imagine that since these are unit vectors, their heads lie on the unit circle. In other words, the dot product between them is just going to be the projection of one onto the other. So by the formula we have seen before, the dot product is length of A times length of B times the cosine of theta. And I'm leaving everything here in the absolute value. But this, since these are unit vectors, the length of A is equal to 1 and the length of B is equal to 1, this is nothing but the absolute value of the angle cosine of theta, which is, well, it's less than or equal than 1, which is the product of A dot B. So what I'm saying here is that Cauchy-Schwarz holds for unit vectors. And that's the end of step one. Our second step will be, okay, I'll take any vector, u and v. But we can apply step one to this more general case by using the following trick. We can normalize the vectors. So instead of u, I'll define a new vector a, which is u over the norm of u, and v will be v over the norm of v. And now these two, a and b, are unit vectors. For example, if I take the norm of a, this will be the norm of u divided by the norm of u, which is the scalar that I'm multiplying by, and that's equal to 1. So let's combine these vectors a and b and apply the Cauchy-Schwarz inequality in case 1 to a and b, because those are unit vectors. That's the same as saying that u over the norm of u dotted with v over the norm of v is less than 1. But then if I multiply both sides by norm of u times norm of v, I get that the absolute value of u dot v is less than the norm of u, norm of v. And sorry, this should be a less than or equal to. Yeah. Okay, so this tells us exactly that Cauchy-Schwarz holds for general vectors. There we go. We will use the Cauchy-Schwarz inequality to prove another inequality, which is very intuitive. It's called the triangle inequality, and it reads as follows. If I take any two vectors, uv, then the length of their sum is going to be less than or equal to the sum of their lengths. The picture you want to keep in mind is this triangle over here. Here we have, I drew u and then v attached to it so that my quantity a is nothing but the length of u, and b is the length of v, and c is my length of u plus v. You see that whenever you can arrange things in a triangle like this, the length of c is always smaller than the length of u plus the length of v. That's why this is called the triangle inequality. It's always smaller. It could be equal only in the case in which the triangle is just flattened out completely and c, a, and b are actually parallel. That's what we're proving. But using linear algebra, we can prove it as follows. A computation that we did last time told us that you can write u plus v norm squared as u squared in norm plus 2 u dot v plus norm of v squared. This is, I remind you, passing through the fact that that's the same as writing u plus v dot u plus v. And that will give us the second term here. Now, I want to write an inequality here, and I'll do it in different steps. The first one will be to replace the dot product with its absolute value. For sure, if I have u squared and v squared, but then I have u dot v, that's going to be smaller than u squared plus v squared plus u dot v in absolute value. Then the second thing we're going to do, since we have an absolute value here, is to use the Cauchy-Schwarz inequality. Applying the Cauchy-Schwarz inequality here gives me u squared plus 2 times norm of u, norm of v plus v squared. And that's just the square of a binomial. That's exactly norm of u plus norm of v squared. You get a double product when you FOIL this out. Now, let's have a look at what we proved here. We have norm of u plus v squared less than or equal than norm of u plus norm of v squared. These are two positive numbers. The square of one is bigger than or equal than the square of the other, so I can take the square roots of both and still preserve the inequality. Taking square roots, I get that norm of u plus v is less than or equal than norm of u plus norm of v. And that's my triangle inequality right there, which is the same as it's stated here. Okay, I'll see you in the next video with more applications of orthogonality.